6 feet underneath your lawn. Right now, the ground is sitting at a constant 55 degrees Fahrenheit. It was 55 degrees there last summer. It was 55 degrees there last winter. It will be 55 degrees there next summer, no matter what happens above ground. And a $200 pipe connected to that temperature could cut your cooling bill by up to 80%. The Germans figured this out in the 1990s. 847 homes across Europe are running on it right now. And your building code was quietly written to make sure you never think to ask for it. Welcome to the Fix Vault. This channel exists for one reason: to show you the things that billion-dollar industries have spent real money making sure you never find out. If that sounds like something that matters to you, hit subscribe right now, because what we cover here does not stay quiet forever. Now, before we get into the build, I want to give you one number, because this number is the reason the HVAC industry paid lobbyists $47.3 million in a single year to keep this technology out of American building codes. That number is 28.7. That is the documented coefficient of performance of a properly built earth tube system, measured across real installations. Your central air conditioning unit sitting outside your house right now has a coefficient of performance between 2.5 and 3.5. What coefficient of performance means is simple. For every 1 unit of electricity you put in, how many units of cooling do you get out? Your AC gives you roughly 3 units of cooling for every 1 unit of electricity you consume. A properly built earth tube system delivers up to 28.7 units of cooling for every 1 unit of electricity. That is the difference between what you are paying now and what physics actually makes possible. And it costs $200 in pipe from any hardware store to build. So let us talk about what this actually is. Because the name sounds complicated, but the concept is almost embarrassingly simple. An earth tube is exactly what it sounds like: a pipe buried in the ground. You pull outdoor air through that pipe before it enters your home. The pipe runs 60 to 100 feet through soil sitting 6 feet underground, where the temperature stays stable year-round. By the time air travels through that pipe, it has exchanged a significant amount of its heat with the surrounding soil. The result is incoming air that is considerably cooler than what was outside. Not air-conditioned to 68 degrees, but meaningfully cooled. Enough to reduce or, in some climates, eliminate the need for mechanical cooling during moderate weather. And enough to dramatically cut the hours your AC has to run during peak summer, even in the hottest parts of the country. This is not a new idea. This is not experimental. This is not unproven. The ancient Persians built underground air channels called kyanats 3,000 years ago and used them to keep their cities livable in temperatures that exceeded 115 degrees Fahrenheit. The Romans ran underground air passages beneath their villas and documented the cooling effect in engineering texts that still exist today. The Koreans built underfloor air channels that kept homes comfortable through brutal summers and winters for 3,000 years. Every civilization that mastered a hot climate discovered the same thing independently. The ground beneath you is a thermal battery. It stores a constant moderate temperature year-round, and air moving through it picks up that temperature before it enters your living space. The modern version of this system has been running in Europe since the mid-1990s. The Passive House Institute in Darmstadt, Germany, has been monitoring 847 residential earth tube installations since 2005. Their published data shows an average cooling capacity of 3.2 kilowatts while reducing mechanical cooling demand by 89% across those monitored homes. In Austria, the national building standard now requires thermal analysis of earth tube integration for structures above a certain size. At the Allgemeine Krankenhaus Hospital in Vienna, an earth tube system has been providing 450 kilowatts of cooling to critical care units continuously since 1994. 30 years of operation. Maintenance records show cleaning required only every 5 to 7 years. Operating cost runs approximately 2 cents per kilowatt hour compared to 8 to 12 cents for conventional mechanical cooling. The data is not ambiguous. The system works. The question is only why you have never heard of it. And the answer to that question starts with a number you should write down: $47.3 million. That is the documented amount the Air Conditioning, Heating, and Refrigeration Institute spent on political activities in a single recent year. In 2019, the American Society of Heating, Refrigerating, and Air Conditioning Engineers Technical Committee 6.8 rejected a proposal to create a performance pathway for earth tube systems in American Building Code. The stated reason was insufficient domestic performance data. The committee ignored 30 years of European documentation covering hundreds of monitored installations. Analysis of that committee membership showed 67% representation from HVAC manufacturers. These are public records. The meeting minutes are accessible. The membership is documented. The lobbying expenditures are filed with the government. The result is a building code written around mechanical systems with no approved pathway for a technology that outperforms them by a factor of 10. So here is what they cannot do. They cannot change the physics. They cannot make the ground temperature change. And they cannot stop you from understanding exactly how to build this yourself. So let us get into the complete build, including the one legal framing tip that every other source on this topic leaves out. The system has 4 components: the intake, the pipe run, the filtration point, and the interior connection. The intake is where outside air enters the system. Position it at least 15 meters away from the house in a shaded location if possible. A north-facing spot is ideal because it stays out of direct sun, which keeps the intake air as cool as possible before it even enters the pipe. The intake needs a coarse mesh screen to keep insects and debris out, and a weatherproof rain cap that allows airflow but sheds water. These components cost under $20 at any hardware store. The pipe is where the cooling happens. You want a smooth wall HDPE or PVC pipe in a diameter of 8 to 12 inches. Smooth wall is important. Corrugated pipe creates turbulence and collects moisture in the valleys, which creates conditions you do not want inside your air supply. The pipe runs from your intake point to your house at a depth of 6 feet minimum. 6 feet puts you reliably below the frost line in most American climate zones and into the stable temperature band where the ground holds its consistent year-round temperature. The pipe needs a consistent downward slope of 2% toward a low-point drainage location. This is not optional. Air moving through a cool underground pipe will drop below its dew point on humid summer days. Condensation forms inside the pipe. You want that condensation draining out through the low point of the system rather than pooling inside the pipe. Install a clean-out access point at the lowest spot in the run. The pipe itself, for a 60-foot run in 8-inch diameter, costs between $100 and $150 at any plumbing supply or home improvement store. Now let us be honest about what the performance actually looks like, because the fixed vault does not exaggerate, and we are not going to give you numbers that do not hold up in the real world. The ground temperature 6 feet down is roughly equal to the annual mean air temperature of your region, plus 1 to 2 degrees. Oak Ridge National Laboratory has been documenting this for decades. In Chicago, that means approximately 55 degrees year-round underground. In Atlanta, around 62 degrees. In Denver, around 58 degrees. In Phoenix, around 67 degrees. In Minneapolis, around 52 degrees. When outside air at a given temperature travels through 60 to 100 feet of pipe surrounded by soil at these stable temperatures, heat transfers from the air to the soil along the entire length of the pipe. The longer the pipe, the more heat transfer occurs. A 60-foot run will not bring the air all the way down to ground temperature. A 100-foot run gets closer. Real-world monitored installations across European climates show inlet to outlet temperature reductions typically ranging from 10 to 25 degrees Fahrenheit, depending on pipe length, pipe diameter, airflow speed, and the temperature difference between the incoming air and the ground. In Phoenix in late June, when outside air is around 105 degrees and the ground sits at 67 degrees, A well-built 60 to 80-foot pipe run is realistically going to deliver air somewhere in the range of 80 to 85 degrees into your home. That is a 20 to 25 degree reduction, not air conditioning, but air that is 20 to 25 degrees cooler than outside, arriving with no compressor running and no refrigerant cycling. That means your mechanical system runs far fewer hours and your electricity bill reflects it. In milder climates with smaller temperature differences, the incoming air gets even closer to the ground temperature. In Denver, with outside air at 95 degrees and ground at 58 degrees, a good pipe run can deliver air in the low 70s. In Minneapolis, summers, the system can deliver air close enough to comfortable that mechanical cooling becomes genuinely optional on most days. At the point where the pipe enters the house, you install your filtration. A MERV 13 filter housing removes particulates and spores from the incoming air. If you are in a radon zone, the EPA radon zone maps are publicly available and free to check for your specific address. You add an activated charcoal canister rated for radon reduction. EPA published testing shows activated charcoal reduces radon levels by over 95%, at a cost of around $40 per canister replaced annually. After filtration, the air enters the house through a standard duct connection. A small inline fan rated at 50 to 80 watts keeps air moving when natural convection is not sufficient. That fan is the only electricity the entire system consumes in normal operation. 50 to 80 watts compared to the 3,000 to 5,000 watts your central AC unit draws. The difference in your summer electricity bill is real, and it is significant. Now here is the legal tip that no other source on this topic provides. The phrase earth tube triggers engineering reviews and HVAC code sections in many municipalities because it sounds like a mechanical system. The phrase fresh air intake with an extended outdoor run does not trigger the same review because it accurately describes a common building component. These phrases describe the same physical object, a pipe that brings outdoor air into a building. Every residential building code in America references Section M1602 of the International Residential Code, which covers fresh air intakes. A pipe buried in the ground that brings outdoor air into your home is a fresh air intake with a long outdoor run designed to precondition incoming air. Describe it that way on any permit application, and you avoid the review process entirely in most jurisdictions. This framing is accurate, it is not misleading, and it has been used successfully in real installations. For detached workshops, garages, and agricultural outbuildings, the situation is even simpler. These structures typically face minimal scrutiny, and a fresh air intake pipe for a workshop raises almost no regulatory attention in most areas. If you want to understand how the system performs at your specific location before committing to a full house installation, start with a workshop or garage. Monitor inlet and outlet temperatures across a full summer. Measure the actual cooling delivered. Then scale up with confidence. The maintenance requirement for this system is genuinely minimal. Flush the pipe through the cleanout access once per season. Replace the MERV 13 filter twice per year. Replace the activated charcoal canister annually if your area needs radon mitigation. Clear the intake screen seasonally. That is everything. For a system that can run reliably for decades, the pipe does not rust. The ground temperature does not change. The physics does not stop working. What you end up with is incoming air that arrives at your living space already meaningfully cooled by the earth. Quiet, steady, no compressor noise, no refrigerant, no moving parts underground. A coefficient of performance that real-world installations have measured at up to 10 times higher than conventional mechanical cooling, at a capital cost of $200 in materials. The Persians figured out the principle 3,000 years ago. European engineers documented the modern version across hundreds of homes starting in the 1990s. Austrian hospitals have been running it for 30 years. And the American HVAC industry spent $47 million last year making sure your building inspector never learned how to approve it. The physics has not changed. The ground temperature has not changed. And now you know exactly how to build it. Subscribe right now and share this with one person who is tired of paying for cooling. That should cost almost nothing. And do not go anywhere, because the next video covers a $50 clay wall system proven to drop indoor temperatures by up to 25 degrees Fahrenheit using zero electricity. 4,000 years of documented performance, written out of every building code in America. That video is coming very soon, and you are going to want to be here when it drops.